you remember when I tried to make a one-wheel balancing robot which almost worked? It balanced on one omnidirectional wheel which had motorised little wheels all around it so it could move in all directions and balance on the spot. However, it was quite chaotic and it was very hard to tune to balance properly. I also made various other one-wheel balancing robots using control moment gyros and also reaction wheels. You can check those out along with other balancing vehicle builds that I can actually ride on in my balancing robots playlist. The previous 2-axis omni-wheel used a system of differential drive to control either the whole wheel or control just the little wheels around it. This meant that there were 2 motors driving 2 pulleys on the wheel. When both pulleys were driven, the whole wheel turned, but just one pulley drove the little wheels, so the difference between the 2 pulleys controlled either the whole wheel or the little wheels. The little wheels are driven by twisted belts from some internal pulleys driven via gears from a central gear which is attached to one of the driven pulleys. This was a pretty simple solution and it didn't have too much backlash. This robot was pretty unstable though, so in this video I'm going to improve on it. One thing I found with balancing vehicles is that they're a lot easier to tune to get them to balance really well. This is essentially because bigger, heavier things fall over slower. If I try to balance a long stick on my hand with some mass on the top, for instance, it's a lot easier than trying to balance a pen on my hand. This is because the larger mass has higher inertia, so basically it wants to stay still for longer because it takes more force to move it. So, as well as making some other key improvements, the plan is to make the robot much bigger than before. The new wheel is exactly double the size, making it around 460mm or 18 inches in diameter. So I prototyped up both of those pulleys with a belt on the idlers so we get good tension on the belt and we get the right spacing to make the wheel round. And of course we've got those slanted idlers just like the first one. Eventually the tops of those will go into the top of the mechanism. As usual, most of this project is 3D printed, so thanks to my 3D printing sponsor, which is Lolsbot 3D Printers, who've supported my channel for nearly 11 years with 3D printers. I'm using the Lolsbot Mini 3 here, printing TPU to make 16 halves of tyres to go on my 8 little wheels. The rest of the parts are Pro PLA Plus from 3D Fuel, who also support the channel. So these are some of the pulleys with the gears on, some of the mounts for the axles for the wheels, and also the mounts for the idlers, which are built into the same part, which fits top and bottom. This is the big gear that drives all of the little gears and wheels that go around the outside, and all of these gears are printed with lots of support material due to overhangs. Thanks to 3D Fuel for the filament for this project, you can now get 10% off at 3dfuel.com with my special code and link, and I'll get a small commission. The wheel is twice as big this time, so it doesn't actually fit on any of the 3D printer print beds. So I'm cutting out some plywood parts and then we're going to stick those grey 3D printed parts into recesses to make up the whole wheel. So this is just 18mm plywood and I'm CNCing this out so that we've got all of the dimensions, all of the holes and all of the recesses so that we can make up the whole wheel structure. So that leaves me with a top and a bottom which both have recesses in to put 3D prints in which fit all the way around for the 8 wheels. I also made some HTD profile pulleys and some retainers that go on either side, and these all fit onto 3D printed hubs very well indeed. The tolerance seems quite close here, and that makes up a lovely pulley to drive each side of the wheel. And I painted all of those parts black so they match the rest of the aesthetics of the machine.
So now, of course, we need to repeat this mechanism around 8 times using these tops and bottoms. The only issue is that the idler axles are at an angle, so it's going to be very difficult to push those on top of each other with those being at an angle. So what I should have really done is drilled some holes in the base with a CNC so that we can push them in afterwards or during assembly. So I've made a drill jig, which is another 3D print I can pop in there, and then we can drill through and put all the missing holes in.
So with all the tops and bottoms fitted to the tops and bottoms, it's now time for some assembly, and that means putting one half on top of the other half and getting all of the mechanism inside it. So now you can see that my idler stumps align, and that means I can push the idler axles in from the holes in the bottom that I made. It's time to assemble the little wheels, which consist of a TPU tyre and a hub which bearings fit in. You'll notice a lump on the hub and that locks into the tyre. It's actually very difficult to get the tyre on because they're very, very tight. So use some pliers to just get it on and then push it down hard and it should snap into place. And we need to do that on both halves. There are 8 little wheels and each one of course has 2 TPU tyres. And of course we've got the intermediate pulleys which have gears on that mesh with the central pulley, and that's how the whole mechanism hangs together. However, this is actually very difficult to assemble in stages from the top to the bottom because the gears are locked together. So for that reason I've made the big central gear in 2 halves so that we can put one half in, the little gear, and then put the big part on top. Thanks to Simply Bearings for the bearings for this project and lots of other projects. Check out simplybearings.co.uk for all your bearing needs. There are lots of bearings in this project, some really big ones for the tops and bottoms of the hubs, and of course bearings for the top and bottom of every pulley and every little wheel. One of those hubs fits onto the piece of plywood that has a bearing for the middle gear to spin, a little retainer to hold it, and then a hub goes on that, which is fixed on, and that's for the pulley to spin the whole wheel. So that's bolted all the way through with some M8 studding with lock nuts on, and those are also the axles which make up the axles to hold my intermediate gear stroke pulleys. So first of all I'm going to put in that big gear in the middle, and then we can go round putting all of those pulleys on which mesh with it with the gears which are built into them.
So all those gears mesh rather well together, which is good to turn each of the 8 wheels, but now we need to put the actual wheels in with the twisted belt and the idlers. And once we've done that, then we can put the other half of this big gear on, and then put the top on, and hopefully then push the idler axles through into the top, and that's how we're going to assemble it.
Here's 2 stages assembled with those twisted belts. It kind of runs okay, but it will run much better when the idlers are in to hold those belts in the middle and hold the belt tension, otherwise they catch on the wheels. So it's quite hard to get this together. We have to put the intermediate pulley stroke gear in with the wheel with the twisted belt on without the idlers, and then mess around trying to get a washer on this axle, try to get that aligned with the bearing in the middle of the little wheel, and then screw that all the way in. Then mess around getting another washer in the other end and continue screwing that in until everything's assembled. And then hopefully it should run quite freely. However, I can't turn the middle gear much because the whole thing jams, and that's because those twisted belts are getting caught on the side of the rubbery tyres. So we need to put those idlers in, and then hopefully it should run much freer. The idlers, as you imagine, are also 3D printed, and they have a bearing in each end which fits on a 6mm axle, which I can now screw in through the holes that I made in the bottom, and then that allows us to put the idlers on. This itself is a bit of a fiddle because we have to push the belt out of the way, make sure the bearings don't come out, so for now I'm just putting some nuts on the top so that they don't ride out. And of course we've got 8 pairs of those idlers, each with 2 bearings in, fitted all the way round on each of our assemblies. So now I can turn the whole thing round and round and round and round in the same direction without the belts getting caught and without anything jamming. There is quite a bit of friction, but on the whole it seems like it's probably going to work. And there's hardly any backlash in there. There's a couple of gaps in between the gears in the middle, but otherwise it's actually pretty backdrivable. There's hardly any dead spot.
So that's looking all right. I can turn it. There is a bit of friction, but obviously this gear's not held in the middle properly as well because the bearing's not on there. And we do have these massive pulleys that are going to pull it round, so I think it's actually going to be fine. All we need to do now is put the top on and screw through all of those diagonal idler axles into the other half and take all the nuts off, and then we'll be able to actually put the pulley on and see how it looks then.
So now of course it's time to put the top on, which has got the corresponding parts for the idlers, and that needs to go on top of there.
But before we assemble that, it's time for a quick ad from the video's sponsor, which is PCBWay. PCBWay is a one-stop shop for PCB manufacturing, assembly, but also other types of manufacturing services, including contract manufacturing, all under the same roof. PCBWay manufactures all sorts of boards, including standard fiberglass boards, but also aluminium PCBs, flexible PCBs, and rigid flex PCBs, which are part rigid and part flexible. But PCBWay don't just make PCBs, they also provide parts manufacturing services, including online CNC machining, sheet metal fabrication, 3D printing, and injection moulding. PCBWay's 3D printing services include SLS, SLA, DLP, FDM, in a variety of materials, including various resins, nylon, PLA, ABS, TPU, PEEK, and more. There are various surface finishes available, including painting and even electroplating. Their CNC machining services include a wide variety of materials, including aluminium, stainless steel, and various plastics. They can fit inserts and tap threads, and provide a whole variety of surface finishes, including brushing, painting, powder coating, and anodizing. PCBWay actually made some aluminium parts for my last project, which was the omni-directional ball wheel bike. These were just CNC aluminium plates, but they can of course make multi-access 3D CNC parts as well. Find out more now at PCBWay.com, and I'll put that link in the description to this video as well.
It was quite a fiddle to get it together and get all those idlers screwed through with washers on each end, so here it is assembled, and you can see that seems to be working quite well. There's still hardly any backlash, there is some friction, but I've got that massive pulley to turn so that I can turn those little wheels. It's quite an effort, but I think it's going to be okay. So of course we've got an axle sticking out of one side now and a hub to put a bearing on the other side, and the reason for that will become apparent at some point later in the video. And if I turn one of those pulleys against the other one, then it makes the little wheels move so that it can move sideways. Otherwise it operates like a normal wheel.
Well, it's all together and it works. It's quite high friction though, turning those little wheels, and I think that's down to the rubbery belts that I used, which are HTD5 belts. In the old wheel I used T5 pulleys that are polyurethane, so these are a bit more grippy on the edge of the pulleys. But we'll see. We're going to use a 2 kilowatt motor to power both the whole wheel round, and the differential drive is a separate motor to drive this pulley to drive the little wheels with a reduction, so hopefully there'll be enough power, but we're not going to know till we put the rest together.
The rest of it looks like a big frame made of aluminium extrusion. I've got 2 brushless motors there and 2 intermediate pulleys with a 2:1 reduction. As usual, I'm going to be using 40/40 extrusion for this project with T-nuts in the slots that we can put a bolt in, and that means we can bolt down pieces to it. So I've already fitted these ends which hold the wheel. One has a bearing for that hub, and the other one has some spacers and then an axle. And that one with the spacers and the axle fits right in the middle and fits into the bearings that we already fitted in the wheel so that it spins nice and freely. The other side fits onto the hub, and I've put in a crossbar or 2, and I've fitted my intermediate pulleys, which now run really freely to spin that whole wheel. But of course one is the differential drive for the little wheels. It's time for some motors, which are O-Drive branded 100 kV motors, which are pretty chunky, and we're using the O-Drive S1 brushless motor driver. There's a magnet on the back of the motor and a magnetic encoder on the board, so these get sandwiched together to control the motor. It comes with the mounting plates, and that allows us to control position, velocity or torque. I've got one of those to drive each pulley. I've mounted them on some prints, I've put pulleys on and big chunky wires.
So I've got one motor fitted, and that is the motor. It's got a 2:1 reduction here. It goes onto this pulley from the O-Drive, and that's the one that turns the little wheels. The other motor isn't fitted yet, so this is free to spin round. So let's power this motor up and see what happens. Just going to give that a bit of velocity. So obviously, because the other side isn't held still and it's quite high friction, it's turning the whole wheel. But if I grab this, oh yeah, there we go. We can see just the little wheels spinning. So that's all right, and it's drawing under 10 amps. 50 volts, so let's go right up here. So we're going up to 24 turns a second on this motor. These are still going. We've got about 15 amps. Let's go right up 60 turns a second. And we're under 20 amps on the motor of 50 volts. And these are definitely spinning fast enough to balance, I think. So we should probably brace the other end of this motor. I've got a little piece that fits in the middle to hold that, so it's not just strained on this plastic bracket. And then we need to put the other motor on as well, and then we can do a differential drive to either drive the whole wheel or drive the little wheels.
I made a stand to put this in, which is going to make it much easier to tune and sort out all of the mechanics rather than the wheel resting on the ground, and I can tilt that forwards and backwards, and also sideways, so I can test everything about its dynamics. I fitted the other motor, and I fitted the little piece in the middle that holds the other end of those pulleys, which have bearings in the end, and a little axle. My electronics are powered by a pair of little lithium batteries, and those switch on the electronics, and they also have a separate switch that power a relay to turn on the power to the O-drives. There's a regulator that powers my Teensy 4, and that's the main microcontroller. I've also got the B&O 086 IMU, which is going to measure the angle. And I've got some pots to trim each axis, a button to initiate the O-drive, and an overall volume control so I can turn up and down the gain. This is the CAN bus transceiver for the O-drives, and we've also got a mystery connector that we'll talk about later. The electronics are fitted right at the top. Below that we've got 2 lithium batteries which are 6S each in series, so that gives us around 50 volts to power this, and everything else is wired in with power, CAN bus, and everything else is assembled. So just looking at the inertial measurement unit data, this inertial measurement unit is very good. It's an I2C device or SPI, and I found this is giving very, very accurate results in both axes, and I've used this in a lot of projects recently because the data is so good. We're going to be using a PID controller to make this balance, which I've used in a lot of other projects, and there's an Arduino library for that. Proportional is the first term, and that literally means as you lean further and the angle is bigger, we multiply that value and give it to the wheel velocity. But we need much more than that to balance.
So I've just put some proportional gain on, so literally a multiple of the angle to the wheel velocity for both directions. And actually this is looking very promising. We've still got quite a lot of tuning of PID parameters to do that I'll talk about in a minute. But for now, I'm actually very hopeful this is going to work really well. There's several other things we need to add to it as well. And we also don't want to be running on this carpet. So let's go to a smooth floor, see how well we can tune it. Wow.
The second term is the integrator, which is really important for balancing robots. So the integrator is the area under the graph. So if the angle is constant and time goes on, then the area increases, and that causes the output to increase, and that causes the robot to accelerate to its target. If the angle increases, then the output increases and increases because that area is getting exponentially bigger, so that causes lots of acceleration. The derivative term causes short, sharp motions in response to the angle, so that damps any overshoot. All of those three terms get summed together, and then we have to tune them, which is a bit like focusing a camera with three lenses, just to get it perfect to balance. And yes, there's an Arduino library which allows you to specify the inputs and outputs and the gains for each of the three terms. So I've done some PID tuning on those controllers for both axes, which are separate PID controllers, of course, with separate inputs from the IMU for the two axes and separate outputs to the two O drives. So it kind of works okay. Most of the time it'll balance and it looks pretty good, but there are some issues where it runs away with itself, and that's quite inconsistent depending on the location or the rotation of the big wheel, and I'll come on to that in a second. If I push it quite deliberately, then it will actually go okay, but then I guess it's a bit like a unicycle in motion, which will stay upright, or any one wheel or anything that balances that's commercially available with one wheel, because we've got the dynamics of rolling a coin on its edge, which automatically stays upright. So this isn't a terribly good test, although it does drive quite smoothly and quite consistently if I do that. So I'm not too unhappy with it. One of the issues with this at the moment is that I made all of these little wheels kind of cone-shaped, so that basically the circumference of the big wheel is consistently round, rather than having lots of wheels which are very blocky and lots of squares around it. That does mean that the small part of those wheels is smaller than the big part of the wheel, and in fact the big part is 50% bigger than the small part, which means that depending on the location of the whole wheel, travelling sideways is sometimes 50% faster. That makes it very difficult to tune because my output sideways varies by 50%. So to combat that, we've got another magnetic encoder and a magnet, and that is fitted into the wheel hub, which is why I put a bearing and a hub on one end rather than an axle sticking out. So that is the magnet attached to the whole wheel, and then we've got this magnetic encoder that fits in just there. So now we can measure the angle of the whole wheel, and then we can work out what position it's in, and then we can go and vary the sideways axes, so those little wheels vary in velocity depending on which part is touching the ground. So here is the whole output. The blue line is the 360 dropping back to 0 as it wraps over, and then I've divided that wheel up into 22.5-degree segments for each half of the little wheels. I've then gone and worked out how to ramp up and down the velocity, so this is a 1 and 0 multiplier zigzagging up and down as each little half of the little wheels goes past when it's touching the ground.
So that's about as good as I can get it. I've tuned those PIDs up a little bit more, and also we've now got that variable velocity, which is varying the velocity of the little wheels based on the position of where the main wheel is. So now it's pretty good. It's actually standing on the spot okay. So yeah, that's pretty good. That's much better than I thought it would be actually. It does still go if I push it a little bit, just like pushing someone on a Segway. And that's probably because the floor is quite smooth, so you know it's quite fast moving. And if we damp it down manually and leave it there, then we should be able to get it to stay on the spot, which is actually quite hard to do. There we go. So yeah, not too unhappy with that so far.
I did a little bit more tuning and I managed to get it to settle in the gaps on the main big wheel. So there it's actually standing almost completely still. So pretty happy of how this has turned out. And if you look closely, you can see the differential pulley facing us rotating slightly separately from the big wheel to operate those little wheels to balance sideways. I thought I'd try and drive it by radio control, so we've got a receiver and my universal DSM remote I built. It's extremely sketchy though, it does run away with itself, and I can vary those set points to try and get it to balance at a different angle, to lean in each direction, just like someone leaning on a Segway, but it's actually very sketchy indeed. It does also rotate on the spot, because if I drive sideways, when one of those pointy cone-shaped parts of the wheel is on the ground or on the verge of being on the ground, then it's like driving with a tapered wheel, and that causes it to rotate. If I was very clever, then I could use that to my advantage to cause it to turn in yaw, but I'm not, and it's extremely sketchy to drive. It does occasionally run away with itself, and I think that's just because the small wheels are so small for such a big robot. But we've got more than enough torque on the wheel, as you can see by the spin out that it did on my kitchen floor. I considered trying to ride on this to see if that was any better, but I thought that the triangular posts all the way round and the little wheels themselves probably wouldn't take my mass. So I want to keep this wheel and use it in another project, which is basically one passive omni-wheel facing perpendicular to the active omni-wheel, so it's like a weird bike that I can ride on that relies mostly on the big omni-wheel for balancing and the little omni-wheel for going forwards. However, the active wheels on the little omni-wheel will allow it to translate directly sideways as well, so that could be quite interesting.